Okay, so here is H-18. The directions are that you're given two functions that are inverses of each other. Okay, so that basically means that they cancel each other out, you could also say like their domain and range are like exactly like opposites. You could say that also. We're gonna do these three things. We're gonna state two compositions that must be true if the functions are in fact inverses. Then we're gonna differentiate each of the compositions. And then we're gonna use part B to represent the derivative of each function. So guys, what we're getting at is a formula that we're gonna use eventually. So in this first one, you are given that W is equal to the inverse of F, okay? So what that means is that W and F are inverse functions. Okay, so means W and F are inverse functions. Okay, it doesn't matter what the little -1 superscript is on. If it's on one of them, it means that they are both inverse functions. Now let me draw your attention to two inverse functions that we've worked with before. So natural log of x and e to the x. Those are inverse functions, all right? Now, what we're dealing with today, we want to think about compositions of inverse functions. And a composition of functions is when you put one function inside of another function. So here, I have put the g function as the input of the f function. All right, so the f function is natural log, so I put the g function e as the input. And guys, hopefully you'll remember from last year, what do a natural log and an e function do to each other? They cancel each other out. Okay, so this is just x. And then we'll do the f function, so the reverse, the f function inside of the g function. So the natural log goes inside of the e function. And again, we did this last year. Those cancel out and you just end up with x. Guys, this is a feature of any inverse functions. The composition, okay, meaning if you put one of them as the input of the other, the composition both ways just ends up giving you x. Okay, they cancel each other out. So for part A, when it says to state the two compositions that must be true if these are in fact inverses of each other, here they are. Okay, so A, it's got to be true that f of W of x just equals x. All right, they cancel each other out. And then it's also got to be true that W of f of x equals x. This is a feature of any inverse functions. Part B, differentiate each composition. So that means to take the derivative of both sides. So part B. Guys, notice I'm going to need chain rule here. So the inside is W, the outside is f of blank. So when we do the derivative of this left side, we get W prime of x times f prime of W of x equals the derivative of x is 1. All right, let me do it over here. So in, out, and if you can skip the chart, that's great. So this time f is on the inside and W of blank. So this is f prime of x times W prime of f of x plus 1. Okay, that was part B. Now part C, use part B to represent the derivative of each function. So I want to represent the derivative of W, and I want to represent the derivative of f. So I want to represent W prime and f prime. Well, guys, here we've got W prime, here we've got F prime. So to get them by themselves, I just divide both sides by, you know, the other factor. So W prime of X is 1 over F prime W of X. And then F prime of X is 1 over W prime of F of X. Okay, so right now, guys, we're just building up to more difficult problems. I'm going to do a second example. I'm going to do it fast. So we're given that R is equal to V inverse. Okay, so this means R and V are inverses. All right, so part A. So R of V of X equals X, and V of R of X equals X. Part B. This time I'll do the derivatives without the chart. So the derivative of the inside is V prime of X. Derivative of the outside is R prime of blank. And then V goes back in, equals 1. R prime of X, V prime R of X equals 1. So V prime of X is 1 over R prime of V of X, and then R prime of X is 1 over V prime of R of X. Okay, guys, that's it.